Okay, so now we're going to talk about attractive forces with dipole-dipole, or specifically the dipole-dipole attractive force, I should say. And so this is going to be the primary attractive force for polar covalent molecules that don't hydrogen bond, because hydrogen bonding is stronger. So this takes the cake over hydrogen bonding. Or I'm sorry, hydrogen bonding takes the cake over this. So if you're ranking them, like, that's going to wash out dipole-dipole. So it's got to be a polar covalent molecule, and if it doesn't hydrogen bond, that means no OH or NH in there. None of those. Okay, so the attractive forces can scale up in two ways. So one of them is just a larger dipole. A more polar molecule is going to increase this attraction. Because remember, it's between positive and negative charges. If the molecule gets more polar, it's going to have a larger positive and a larger negative charge associated with it. So they're going to attract more strongly. They're not going to be all the way to a 1. Maybe it's, a 0.6 instead of a 0.4 or something like that. You're not going to work with these numbers. You don't have to worry about it. And so essentially what you're looking for is just potentially difference in electronegativity. But we're going to do an example here in a little bit. So, we're going to say more polar molecule equals stronger dipole-dipole. And when I say this, I mean, I don't know if I said it before, but we were comparing a group of the same molecule. So if I have a beaker of something, does it have more attractive forces than a beaker of something else? And so the other way, so more polar molecule, and then just like hydrogen bonding, if there are more sites for polarity, say, I guess that gives you a more polar molecule. So it really just boils down to one thing. There's two ways to get here. And that's to have or I guess I should say a larger difference in electronegativity, or more polar regions. So more areas of a molecule that are polar. So for example, we're going to break this down. Let's say we have, and I'm using line drawings. So we have 3 carbons, the middle carbon is bonded to a chlorine, 3 carbons, middle carbon is bonded to a fluorine. These are both polar molecules. They're going to have dipoles that look like so, because chlorine's more electronegative than carbon. Fluorine's more electronegative than carbon. So they're both polar molecules. These aren't going to hydrogen bond. This isn't an FH here. This is an FC bond. That's fluorine going to carbon. Chlorine going to carbon. Okay, so it's polar. So these are going to have dipole-dipole interactions. They don't hydrogen bond. They're not ionic, so that leaves dipole-dipole. They're polar. That's our strongest type of attractive force present on these molecules. And so, which one is more polar? Well, it's carbon and chlorine versus carbon and fluorine. Well, fluorine is above chlorine on the periodic table. In fact, it is the most electronegative element. It is the top right of electronegativity. We don't deal with those pesky noble gases. And so this is going to have a larger difference in electronegativity. It's going to have a more polar bond here, which means it's going to have a more polar molecule. So fluorine is more electronegative than chlorine, so that equals a more polar bond, and in this case that also means more polar molecule. So that's the first example. You compare the polarity of the bonds, in which case you get the polarity of the molecules. There's no other dipole to cancel out, anything like that. The other situation, maybe we have something like this. Okay. These can't hydrogen bond. They're not ionic, but they have polar bonds. They're polar molecules. The dipoles aren't canceling. We have a net dipole here. We have a net dipole here. This one has a net dipole here. Okay. So, which one's more polar? So just like hydrogen bonding. You know, these two sites. That's more opportunity. So you have a partial positive here, partial negative here, partial positive, partial negative. They're going to interact more strongly than just one of them. So this guy's going to win. It's the more polar molecule. It's going to have the strongest dipole-dipole interactions because it has more opportunity for those interactions to take place. So you're really looking for either, you know, more polar locations or stronger polarity in the same number of locations. I'm not going to mix these variables up on you guys. All right. And so again, if there was something that could hydrogen bond, it would beat all of these. If there was an ion-ion compound, so an ionic compound, it would beat all of these in terms of attractive forces. They would have more strong attractive forces than these. Alright, so we got one more left to talk about. So we just finished dipole-dipole. So now we're going to get into dispersion forces. And that's the weakest attractive force. So you only worry about it when you see an absence of this, hydrogen bonding, and ionic compounds. Alright, so we're going to talk about that next.